Okay, good morning, everyone. Thank you for coming, and especially thank you for coming at 8:30 in the morning. This is a challenging time for us to give the talk, but I think this is an absolutely fascinating presentation, personally. The topic is near and dear to my heart. So this is a joint presentation, VMware and Jackson National Life Insurance Company. I'll be joined on stage a little bit later by Wayne Longcore, who's the VP for IT Client Services. This is really a Jackson story. You know, I'd love to be able to claim that VMware came in and did some awesome architectural magic to help, Jackson figure all of this out. Jackson did this themselves, and I actually think it's really, it's awesome, and it's awesome in its simplicity in some sense. But the results that they've seen, I think, that they've shown actually speak for themselves. Now, this is an example of high-performance computing, which is something that is near and dear to my heart. I work in the office of the CTO, and I'm the chief technologist for HPC for VMware. So here's the game plan. I'm going to give you a brief overview to sort of set the context for the rest of the talk, give you a little bit of information about what we're doing around high-performance computing at VMware, talk a little bit about the history of cycle harvesting, and then I'll turn it over to Wayne, who'll take you through the details of what it is that they're doing, how they're doing it. I'll come back, give you some performance information to sort of justify what you've been shown, and then Wayne will take it back over and talk about benefits and the futures that Jackson is looking at. Okay, so let's talk briefly about virtualizing high-performance computing. And by this we mean science, research, engineering, financial services, very, very compute-intensive applications. Our goal in this area is to take the capabilities that we have in the enterprise-class VMware platform and bring those to bear and offer benefits to HPC environments, which are, for the most part, bare metal at this point. There are very few virtualized instances of HPC. So by bringing our capabilities together with those workloads and environments, we've done this with other customers, we've actually shown significant value bringing those two different worlds together. Okay, so just really briefly, what do I mean when I say HPC? So high-performance computing workloads, as I said, are kind of technical workloads, science, engineering, research, finance. They are often extremely floating point intensive. They're often very parallel and very, very data intensive. You can see on the right-hand side a list of the common areas where you would find these kinds of applications. Many of the VMware customers actually have a significant amount of high-performance computing workload. Again, it's usually bare metal and completely separate from their VMware infrastructure. You can see at the bottom here kind of a cartoon showing you the two different types of applications that exist in this space. On the left-hand side, which is the one that's more relevant for this discussion, are throughput applications, where you have many, many processes, which are usually single-threaded, they may be multi-threaded, but the name of the game here is to take this large number of jobs and run them on your cluster in parallel so that you can get them done as quickly as possible. So very close to what Jackson is doing would be, for example, running a large number of Monte Carlo simulations and running those in parallel on that cluster. On the right-hand side, and we won't spend really much time talking about that, is a more complicated application pattern where you have these individual processes that are running spread out across the cluster, but there's a lot of intercommunication between those pieces. Could be millions or even billions of, literally billions of messages interchanged between those pieces as the job runs in order to solve the problem. And usually you have some kind of an exotic special purpose interconnect like InfiniBand or RDMA over Converged Ethernet to get low latencies and very, very high performance. Okay, so why are people looking at using virtualization for high performance computing? And I'm not going to go through this whole list, but the thing to know for people that are not all that familiar about HPC, and it's shown on the left-hand diagram there, is that they have a machine, a large number of machines. They usually run Linux of some sort on that, and then the user's jobs, multiple users' jobs, end up running in the same Linux instance. So if we transition them to the picture on the right, which we all are very familiar with, you're now giving them a per VM experience, right? So user A runs in their own VM, user B runs in another VM. So the benefits that accrue to moving those HPC people into this environment are blindingly obvious to us as virtualization people. but they're actually quite new and quite novel to the HPC folks. So just the idea of heterogeneity, being able to run, say, a Linux instance and a Windows instance on the same box at the same time is not something that they can do typically in their environment, even though it would be very beneficial for them to do that. The other two things that are most relevant for this discussion are the fact that the VM abstraction gives you a security separation. So now if I have jobs running in separate VMs, you're not going to have data leakage between them as you would on the left-hand side where you have jobs running in the same OS instance. And you also have fault separation. So if on the left side, if somebody fills /temp or causes some problem in that OS instance, it will potentially affect all of the users who have jobs running in that operating system instance. And then, as I said, I'm not going to go through all of these. We can also use vMotion for some interesting things. But the main point here is that the VM abstraction actually brings some very nice things to the table when you virtualize these HPC environments. Okay, so in terms of performance, we have these two different classes, the throughput class I mentioned and the MPI class. On the left-hand side, I've just picked out one example which is again relevant to the Jackson use case. This is our benchmarking of a Monte Carlo simulation. And what you can see on the y-axis is a performance ratio. Higher is better. 1.0 means that the virtual is running exactly the same speed as bare metal. If it's lower, it means that we're losing performance. So you can see for the Monte Carlo simulation, which is often used by financial services, that there's no degradation whatsoever. These run at full speed. On the right-hand side, the MPI applications, as I said, are much more challenging. And it's a much longer story about how we do there, but I'm giving you sort of a representative sample. And you can see we have more fluctuation there. We can get up into the high 90%. I could find applications that may have a 25% performance degradation. It's a much more nuanced story. If that's something that you really care about, come talk about to me afterwards, and I'm happy to give you more information about that. Okay, now before I move on, I want to mention one thing. We're mentioning this in all of the talks where we are discussing big data and HPC. At VMworld on Monday, we announced a new vSphere edition called vSphere Scale Out that is specifically and exclusively targeted at big data workloads and HPC workloads. So big data in this case means Spark and Hadoop. So if you have plans to run either of these kinds of workload types, then you should take a look at this SKU. Think of it as a vSphere edition with a few features removed that are not particularly important for HPC, with an extremely different and attractive price point than what you would see for the other VMware edition, the other vSphere editions. Okay, so let's talk a little bit about cycle harvesting. So this is the concept, and it's a pretty old concept, of using spare cycles, often using other people's spare cycles historically. So the sort of canonical example of that would be SETI at home, so the search for extraterrestrial intelligence. And basically the way that works, there's a very large radio telescope in Puerto Rico, Arecibo, that is gathering signals from deep space. And those signals are then taken and forwarded out to machines all over the world. They could be desktop machines in people's houses, people do it on laptops, some people use servers. And what they're doing is running an agent inside of their operating system instances at their local site or at their house. It's often at their house. A lot of private citizens participate in this. And as free cycles become available, the SETI at home daemon takes those cycles, does processing of the radio telescope signals, and it's looking for patterns and other evidence that there may be extraterrestrials out there in the universe. It's been running for quite a long time. They get about 980 teraflops of performance on any given day. So those not familiar with teraflops, that would be 980,000 gigaflops worth of performance. And a flop is a floating point operation per second. So 980,000 floating point operations per second being contributed into this project in order to try to find signals of interest. And you can see about 100,000 active users at any given time. It's a pretty big effort. So they had such a nice success with SETI at home that they generalized that framework, and they created something called BOINC, which is the Berkeley Open Infrastructure for Network Computing. And that hosts a number of projects. They're getting about 110 petaflops of performance from that aggregated mass of compute resources. So 110 million gigaflops worth of performance. You can see about 200,000 active users and over 1 million hosts that are actually contributing cycles to this. So aside from that, more directly in the HPC space, there is a scheduling package that has scavenging capabilities in it, or harvesting capabilities, called HT Condor from the University of Wisconsin. That is used in some cases within high-performance computing community to gather and harvest spare cycles from desktops and from other systems. But again, the approach here is that you're running an agent inside of a guest. And there could be concerns, sorry, not inside of a guest, inside of an operating system instance. It's not usually virtualized. And there may be concerns there. It adds software complexity to introduce that sort of a framework into your environment, and then also potentially, as we said earlier, failure concerns and security concerns. So the question is there another way for VMware customers to actually achieve this sort of thing, a more elegant way of doing it? And I'm going to turn it over to Wayne, who is going to explain what Jackson is doing.
Thank you. Now, if only I can figure out which one. So, at Jackson, first I'll describe our environment. We have a few architectural imperatives at how we present the desktop. And the first is we measure everything based on user experience. We know to the 100th of a second how long it takes to click an email. Whether you're in preview, how long it takes. Whether you open the mail, how long it takes. How long it takes to access your various applications. And we graph that out both based on the geospatial location of the user, the department of the user, and averages across the whole company. It allows us to find problems within applications, but more than that, it allows us to assure that we're providing a better VDI experience than the i7 laptops we provide. So we believe in high-performance VDIs for the end user. We also believe that those VDIs should stay current. So last year, in about 6 months, we upgraded from Windows 7 to Windows 10 because we're in a VDI environment. We're able to do that by snapping off the current VDI, doing the upgrade if there's any problem, telling the user, oh, we couldn't get to yours last night. The truth is there was some kind of a problem, and we end up doing them the next night. We're on Office 365 Pro Plus, the 2016 version now. We did that upgrade in about 6 months as well. We focus on user productivity. We don't believe in spend, a few less pennies, but cost dollars of end user time. So to us, uptime is measured through that same thing. We know as soon as email is running slower, how many dollars per year of wasted time it is. We do that calculation regularly. If your applications run slower, we know what the impact to the users are. But we also then take that same thing into downtime. We measure how many minutes of downtime we have for users, and we turn that back into dollars of user time as well, so that we make our choices in our architecture for speed and for uptime. Based on that, we run a shared nothing architecture. Running a shared nothing architecture, nothing, no software, no control apps, will take one blade down while it takes another blade down. In the last year, we've had one major outage, which is defined as more than 30 people down at a time. That was caused by us pushing icons to a desktop and having somebody not do the full checks on that. And we took, I think, about 300 people's icon away where they had to start an app. We went into a major outage. That's one outage in an entire year. We also, because of that shared nothing environment, have much greater throughput through parallelization. Because everybody is going to separate locations, we achieve much higher throughput than a normal environment, which is bottlenecking through a single failure item. We believe in high core count for peak usage. We don't believe subpar performance is acceptable even 1% of the day. If you believe that 1% of the time it's okay to bottleneck through something, and you figure that there are 2,000 hours of a user's time in a year, that means 20 hours of the year, they reach some subpar performance. And if you reach that subpar performance 20 hours of a year, the user remembers those 20 hours and says your VDIs suck. Pardon the word, but it's just general. People don't like even 1% of the time to run slow because you bottleneck through something. And because of this architecture, we do not believe in expensive, overstuffed rack mounts. We believe that when you spend too much on big rack mounts, you have limited core counts, because very few rack mounts are more than 2 sockets, and you end up with overcommitted buses. However, we also believe in extremely limited memory overcommit. While it is possible to memory overcommit, what we see is when you memory overcommit, your users, especially in the VDI space, suffer performance, and they don't always understand why and what's going on. As a matter of fact, this we learned yesterday in a session. I'm really glad to come to VMworld and learn this. Actually helped us to understand that we probably want to pin our VDIs into memory more, where we've been just allowing them to be managed by the operating system. I think by pinning, we will even see less impact from memory controls and ballooning that occurs, it looks like, well before you reach the full amount of memory on the machine. We spread departments across different data centers so that even if an entire data center goes down, the users of that department have at least half of their users still up while they're booting, and within 30 minutes, those other users are back up. Now, knock on wood, I've been here 5.5 years and we've never had a data center outage. But 2 weeks ago, we actually failed out of one data center, ran for a week purely in the other data center, and then at the end of the week failed back into the previous data center just to show that no user received any negative impact by running out of just one data center. And then we run releveling scripts across our environment based on our sizing factors that allow us to charge back based on the amount of resource you're getting out of this cloud of servers. Every user is paying for the size that they are given. A lot of times people want to charge based on usage, but we view that what we're competing against is laptops. And if you buy a laptop, you don't go back to your IT department and say, well, I didn't use it last week, I don't want to pay for it, right? The VDI is essentially your desktop, you're paying for it, therefore you pay based on your size. We believe that VDI is very much your personal thing, and therefore we don't do any non-persistent VDIs. We are persistent across the environment. We use low-cost components with no bottlenecks to either memory or disk in a hyper-parallel environment. And we cost $255 on average per VDI. That's taking my entire hardware spend and dividing it by my GPUs, my blades, everything that I spend per year. And I stay right around that $250 a user per year for a VDI. And then we believe in differentiated service levels. Not everybody runs at the same size in the environment. Because everything is like a laptop, you can buy an i5 processor, you can buy an i7, you can buy different amounts of memory. Well, we do the same thing. I think a lot of people who run VDIs run this this kind of a thing. We're rather stringent about it, that a bronze grows each year, but the bronze is a 2-core by 5 gig right now with a 100 gig hard drive as far as we're concerned. And we give them between 10 and 15,000 IOs per second in that desktop. A silver, jumps up with a little more memory. Everything grows until you get to that concierge level 4. Any of the concierge have to come and ask me, because we try and keep those few and far between, but there are hundreds of those. And the biggest users we have are 28 cores, 96 gigs of RAM, 8 gigs of GPU, and I think we have a user who's very close to a terabyte of disk. That highest end user actually has the ability to have an Optane available to them, and so you're hitting hundreds of thousands of IOs per second at that level. Our blade design, obviously the Optanes are not in the blades, those are in the few rack mounts that we have. But in our blade design, we run either 8 or 14 core sockets. On top of that, we run 1.6 or 1.92 terabyte local SSDs. And then we run an NFS VMDK, which is presenting that back to the local machine. That is replicated to the other data center such that should this blade go down, the users just get booted on the exact identical peer in the other data center. And then on top of that, with all of those cores, we run up to a 5-to-1 memory or CPU overcommit. Therein, if you've got a 28-core total blade, you might be using as much as 140 cores of CPU. The total environment is made up of 13 enclosures, 16 blades in each, and 16 rack mounts on both sides. Exactly identical, named exactly the same, such that, you know, if you're in the A side, you have an exact identical name in the C side, just with a C at the end. Total environment. And I know this precursor is, you know, rather long, but I'm trying to give you an understanding of our environment. We run 444 hosts. On the dollars I told you, a total of 10,468 cores. And to the cycle harvesters, we hand about half that memory. 71 terabytes of RAM is provided to the cycle harvesters. We're running 50-50 in the data center, so 50% is available, out of a total of 155 terabytes of RAM. The cycle harvesters use scratch disk of 280 terabytes of SSD out of a total 2,007 terabytes, 2 petabytes of disk, for the price I told you. And the capacity going to that disk is 71.6 million IOs per second for the cycle harvesters, and they, at times, really bang on the disk because they're using it as their scratch disk to do these computations. The total throughput to disk, because this is this parallel, is 4 terabits per second. And when we wrote this paper, it was 6,768 this morning. I think it was 7,000 VDIs in the environment. And that grows and shrinks. And then there are 888 cycle harvesters, 2 for every one of those, 1 per socket running on those machines. So let's talk about cycle harvesting. What are we doing and what are we gaining from it? Well, you've already seen this description of how we're running inside of those blades. On top of it, we simply placed 2 Windows 10 user machines that are the size of the cores of that socket. The cycle harvesters are configured such that they're 7 gigs per core, approximately 30 gigs of disk per core, and a 60 gig boot. But again, they're no different than your VDI if you're a user. As a matter of fact, they're smaller than that Concierge Level 4 was. And then they are talking to a distributed file system where they're pulling their data from. Now the DFS it actually became a bottleneck to us. We realized that as we got a little over 7,000 cores, we maxed out the 10 gig coming out of the DFS. And so now we have to have multiple DFS shares in order to feed this environment. So the cycle harvesting, you've seen this picture already, is simply that cycle harvester going direct to disk. So the disks have an NFS VMDK talking to it, and the cycle harvester talking to it. And they access the disk at the same time. So what's the secret sauce? How did this work? And by the way, work seamlessly across the environment. Amazingly, we actually sped our users up by doing this. That's the power of VMware. We didn't slow the users down by cycle harvesting off the cycles. We sped them up. We sped them up for several reasons. For one, the CPUs now are always at their maximum throughput. Josh did some analysis for us, and I think at one point while he was monitoring it, we were using 39 cores equivalent throughput on a 28-core machine because of hyperthreading, because of the way that's so specific to have this various process run per core. It enables that hyperthreading to an extreme. I think it's a pretty good throughput. So what we did is we simply set those cycle harvesters to 100 shares of CPU, while the users were set at the standard 1,000 shares per CPU. That's a pretty simple thing. By setting it at that, the cycle harvester on that 14 core gets a total of 1,400 shares. And now if you've got a full machine and it's got, it's at that 5-to-1 overload, you've got 140 shares, 140,000 shares being used by the VDIs, and you've only got 2,800 total being used by the cycle harvester. So at max load, the cycle harvesters will use less than 2% of the machine, and yet if the users are not doing anything, within milliseconds, the cycle harvesters are using up to 98% of the machine. We run HPC jobs inside of each of those cycle harvesters, not as one big job, but then as HPC jobs that are running a task per core so that they end up using that hyperthreading better. And then all of that is fed by a Windows HPC server, which is pointing back to those DFS shares that we talked about. So with that, we talked to Josh, and he came out to do an analysis on this and to look at, were we really getting what we thought we were getting out of it, because it seemed to just work so well. And Josh, I'll let you talk to that.
Great, thanks, Wayne. So this was fun for me because I had a very naive view of what a VDI environment looked like, in the sense that I thought, at 9 o'clock or 8 o'clock in the morning, everyone comes in, they all start working, they all go home at 5 or 6, so you see, a plateau. You see the usage go up during the day, you see it go down, and it's quiet in the evening, so I expected to see the cycle stealing happening off in the off hours, and that is not at all what we've seen. We did a lot of analysis looking at using ESX top to gather 24 hours of data, looking at various hosts in the Jackson infrastructure, and it was quite different. We saw VDI instances of VDI where they were active in the evening, active in the early morning, active all day. It was everything that you could possibly see. And so it actually looked quite complex. And so what we've done here to make this story a little bit simpler is to narrow in on a period of about an hour to demonstrate to you what the interactions are between the VDI VMs and the cycle stealing VMs that Wayne just described. So let me take you through this. So these first set of charts are showing you we're looking at a single host in this large set of resources that Jackson has. And we're looking at a representative sample of VDI VMs that are running on that single host. And the way to look at this is, this happens to be a host that has, I think it's the gold class of VDI VMs. These are 4 core VMs. And so you see time on the x-axis and CPU utilization using percent used from ESX top on the y-axis. And you can see, some of that complexity that I was surprised to see. You see some of these VMs are, for the most part, pretty idle during this period. Others are cranking pretty high using most of the 4 cores on that particular VM. So it's a mix of different utilization, even within this time slice that we're looking at. So if you take all of the VDI VMs that are running on this host and add them all up, and then also show what the 2 cycle stealing VMs are doing. So recall, this is a 28 core system, so 2 14 core sockets. And what we're looking at here, the red and the blue, are the 2 cycle stealing VMs. Each one of them is configured as a 14 VCP VM. Okay, so you might at first blush think this looks a little bit odd, right? Because I've said that this is a 28 core VM. And if you look, even say on the far left-hand side, and you add up what each of those cycle stealing VMs is doing, each of them is about 14 cores worth of workload. So that's 28. And then you've got the additional maybe 5 or 6 for the VDI workload. What's going on there? That's pretty odd. So it turns out that when we do the calculation for percent used in a situation where hyperthreading is turned on, those numbers get multiplied by a 1.25 factor to sort of account on average for the increased utilization that you get by having the hyperthreads turned on. which is why those numbers don't add up to what you think that they might add up to. So if you look at this, you see a couple things. In this particular time period, you can see that the VDI VMs in aggregate are spiking up in the middle of the plot and then coming back down to a lower level on the right-hand side. And then the two the two harvester VMs, you can see that they're dipping a bit in the middle. They seem to be reacting in response to the VDI, but it's a little bit difficult to see. So one of the things we can do before kind of drilling in on this more is to add all of these up. Let's just add all of these three curves together and see how close we're getting to actually driving 100% utilization on the box. Because that's the name of the game, right? So we want to take the VDI workload, and then we want to add as much harvester capability as possible to deliver the maximum value for the HPC workloads and the maximum value for the hardware that Jackson has invested in. So how does that look? Okay, so again, so you can see the multiplicative factor there, the 1.25. We're essentially driving this to 100% utilization. It goes a bit higher due to turbo in some cases. I didn't mention, but the drop there, if you look back here on this previous slide, you can see that the blue harvester dropped down to 0, and it just happens that harvester didn't, the HPC job scheduler that Wayne was describing just didn't schedule jobs for some period of time into that VM. So it immediately dropped down to a really low utilization. And then it started firing more jobs into it, and it kicked back up again. So in some sense, mission accomplished, right? We're getting extremely high utilization here. So the question is, is it delivering a good experience to the user? And so at a high level, yes, Wayne has no complaints from his users, and in fact, he's saying that his VDI users are experiencing having a better experience now that they've turned on the performance settings for power, et cetera. Okay, so let's look a little bit more closely at this. So this is looking at this 1 hour period. And now what we're doing is we've got the same summation of all of the VDI workloads in the black curve again. And now I've added together the two harvester VMs. So you can see in aggregate what's going on. And you can definitely more clearly see here that as the VDI VMs start to require more CPU utilization, the harvesters give it up. And then the reverse happens. And as Wayne said, this is purely a result of using the share setting at the vCPU level in vSphere. It's just automatically happening. And the really nice thing about this approach is that he's put all of the HPC workload into these separate VMs. So this security separation, which I think is not an issue in this particular environment, but certainly fault separation or any issues around contamination between these two workloads is completely stepped around by using separate VMs. Okay, so let me just show you on the final chart. If I really drill in here more closely, and we're looking at just a 10-minute period, what you can see here is, as I was saying before, as the VDI workload goes up, you can see very, very responsively that the harvester use of the system is dropping. And it tracks very, very nicely. And so then one question you might ask is, as we're continuing to very, very rapidly in VM kernel adjust these priorities based on the shares, is that introducing an overhead? So I don't have the charts to show it, but we did do an analysis looking at context switching rates on the box at the VM kernel level. And the context switching rates are in the range where it's only I think it was a percentage point or two of overhead that's being added by the context switches themselves. So as I said, I think big success here. VDI users are happy. The HPC folks are getting a lot of free cycles from Wayne, and everyone's happy as far as I can tell. So one final note before I turn it back over to Wayne. I mentioned the new HPC and Big Data vSphere edition. That actually doesn't apply in the Jackson case because it's a license that is exclusively for HPC or big data workloads. So in this case, VDI is being mixed with HPC and big data, so that doesn't apply. But I also want to mention that, and this is an important point, so the addition of vSphere that underpins a Horizon deployment is vSphere Desktop. And vSphere Desktop is restricted to running desktop VMs. That's written into the EULA, and it's an important thing to keep in mind. Now, Jackson completely meets those requirements by doing the following three things. So they're running a desktop version of an operating system, namely Windows 10. They are running the Horizon View agent in each one of those Harvester VMs. And they're using they're within their license envelope with respect to those harvesters and their VDI licenses. Okay, so I'm going to turn it back over to Wayne to talk about some of the benefits and then on to futures.
All right. So the best thing about this environment is it's super simple. We have a cost savings that is due to avoided cloud costs. If our actuaries had to burst into the cloud, Azure sells the resources that we would need, others sell those resources. The price to get a 7 gig of RAM, SSD based, 30 gig of hard drive plus per core is about 13.3 cents per hour. Well, 13.3 cents per hour doesn't sound too bad unless you're running actuarial computing pretty much 24/7, 365. If you're doing that, that number suddenly is fairly large. And now if you have to add licensed software on top of it for your actuarial computing, which could be anywhere from 2 to 6 cents per hour based on the vendor, you can end up with each core costing you between $1,340 and $1,690 per year per core. If you multiply that by 10,250 cores, you're ending up with between $13.7 million and $17.3 million that we for free are handing back to the organization. So what does it take us to do that? Well, it really takes no new skills on the part of my administrators. They already administer Windows 10 machines. They already distribute software to those Windows 10 machines. They already manage this exact environment. They've just added one more application to it. The cycle harvesting is transparent to both the other VDI users, our support of the VDI environment, our patching, our security, everything. It's transparent to my administrators. It's transparent to the VDI users. But more than that, it's transparent to my HPC users. They still do things the same way they do on our dedicated grid. It increased our virtual infrastructure reliability. That one is kind of an interesting benefit. And why did it do that? Because now we have something running on every machine 24/7 when users aren't, that looks at all the various components and really bangs on the system. And if anything goes wrong, we know immediately. Plus, it enabled us to pay the one cost of all of this to us is we added one administrator who comes in at 5 a.m. because we don't normally run administrators in the middle of the night for desktops. And he then makes sure that everything is right. It actually created a better VDI experience for our desktop users. This was one that we did not expect. When we first spooled this up, my own people were all running in this environment, and the guys are sitting here smiling really big because we came out and said, okay, how much did this hurt? And the responses were, it seems to be running faster. Why? Because now you're pushing that chip always into turbo mode and it's never ever sleeping. And in a VDI environment, quite often users quit doing things and the chips weren't always bursted to their maximum speed. So we actually end up with a better VDI experience. And in those charts that Josh showed, at one point, it was at, I think, 39 cores on a 28-core machine, equivalent throughput. And lastly, what this really did for us at Jackson is it enabled our actuaries to go beyond batch-style thinking and start to think as though high-performance computing is like a PC app. They no longer issue a job that's going to take 24 hours. and the next day come back and get it. Now they can issue a job and have it come back in 8 hours because they've got that many more cores, or 6 hours. Let's talk about the futures of what is coming in this same environment. We are beginning to harvest our GPU cycles because across that estate, we already have 660,000 AMD GPU stream processors in the money we talked about. By this time next year, we'll have over 1 million stream processors. Now, from our calculation, and AMD may tell me, these are not good numbers, but we seem to think, using OpenCL code, that one stream processor seems to be the equivalent of about 1/16 of a Xeon core, at least our current Xeon cores. So 1 million stream processors is about the equivalent of 60,000 Xeon cores. We're testing using OpenCL to have our algorithms run both against the cores and the GPUs, and to be able to do those at the same time. Now we will not release this until the middle of next year. But if we get this right, it's actually fairly easy for us to hit half of our GPUs and to be at 30,000 core equivalents. And our biggest problem is, as I mentioned, at 7,000 cores, we suddenly started having 10 gigabit throughput problems from the input data. Well, at 30,000 cores, we're going to have even bigger problems. We're getting into the throughput issues instead of just the simple stuff, right? With those 1 million stream processors, our biggest problem becomes internal to our machines, using our buses well enough to feed them full time and get the data back out full time. So actually, we'll probably in the middle of next year start to shift away from using our Xeon cores to do the compute, and shift more to using our GPU cores running OpenCL. We did a computation, and if we can get to all 60,000 core equivalents and think of that in Xeon cores, it's kind of an interesting number, because for our $250 a user per VDI, we will be returning $100 million in cloud equivalent cost. And I think that's a pretty good benefit to the company when I've added one administrator and I've not impacted my VDI users. As a matter of fact, from what we're seeing, we've made it better for them. And VMware has provided us with an easy way to cycle harvest those resources back and hand them back to the company. So that's all that we had in as far as the presentation, but we're open to questions, and I think both Josh and Josh is more the expert than we are. I think we're just lucky that this worked this well. Josh has a fairly extensive history in high performance computing, and that's why we asked him out to really analyze the environment.
You're too kind, Wayne. This is all Jackson. They really know their stuff. Questions? There's a mic up here if you have any.
Fascinating talk. I loved it. You talked about how the CPU usage of the harvesters and your VDI, everything, peaks and valleys will run up. What about memory?
Sorry, what about?
Memory usage.
Yeah.
When we were on that, if I go back to this slide, we're rather strong sticklers in our, discussion that we do not memory overcommit. So if I get all the way back here, that extremely limited memory overcommit, the reason for that is if you get into memory overcommit, you end up slowing things down. So because we run 50-50 in both data centers, as far as usage, so that when we fail over, we can run. Once we're in a failed over situation, we turn off the cycle harvesters, right? So that memory is now freed up. And then the users that fail over are using that memory. And then we pin users to the memory. We don't pin yet, but we will soon because of what we just heard, because we think that that may actually gain us a little bit more performance for the users. but we run with enough memory for every user in every environment they're in. And we run that levelizer to make sure that's the case.
Okay, so your overall memory allocation per system is less than how much CPU you're allocating, because your CPU goes to, when your CPU goes to 100%, what's your memory usage? Do you know, are you?
Well, so I think you said that half the memory is being used by the harvesters.
Okay.
Yeah.
Right. So, and CPU usage doesn't really impact memory usage, right?
Right.
You pre-allocate the memory and understand what it is, yet we overcommit CPU considerably because
Right.
users don't use the CPU all at the same time.
Thanks, Reza. Anyone else? Great. Thank you very much for coming.
All right. Very good.
Yep. Very nice.